So this is a follow-up module to driven oscillations, which we already looked at. And so what I want to do is show you that with the help of some small tweaks around the problem we worked out, there are many flavors which come out, right? So this is within the philosophy of this course, which is to explore, to build a model or a method which is solid, take very simple, decisive, solid steps forward, and then use this opportunity created by something that you have laid the foundation for, and do a small exploration around it. And then you see that so many colors come out of this kind of an exercise. So you can think of this as a tutorial, and I would challenge you to pause at various points and actually execute everything on your own, and not just blindly or passively watch me go over my just don't allow me to passively talk through, right? So I would expect that you would pause at various points and then work out your own method and come up with the full analysis, and then watch my video, and hopefully you will have more perspectives, right? And it can all be complementary in nature. All right, so as always, it's useful to start a Mathematica session using this clear, which I have just done already, and I'm going to quickly flash this RK4 method slide. You must have seen it before. So basically the idea is that you first rewrite your equations in this canonical form, and so there is this very nice generic formulation, right, which we have in terms of vectors, where you basically include time also into your x vector, and then you rewrite your differential equation involving as many variables as you need, and of whatever order, right? You have to first recast an arbitrary order equation into a first order equation involving more variables. So that's a first step, and time itself is treated as one variable. So when we do this, we are able to rewrite it as x dot equal to f. So we saw that the Euler method is the simplest, where x dot is approximately taken to be the rate at that particular instant of time alone, and then the improved Euler took an average of the velocity at that point and the following point, and took an average. That itself gave a substantial improvement, and this is equivalent to the RK2 method. And then RK4 method is a more sophisticated method, and turns out to be an excellent approach altogether, because it nicely balances the twin aspects. There is a competition between the number of operations. You don't want too many operations on the one hand, but also you want accuracy, high accuracy, and minimal operations, right? So these are contradictory forces. Somehow experience has told us that RK4 seems to be the most accepted compromise between these two opposing forces. Okay, so I'm going to just load this code. So the details of this code you can find in an earlier video. You can go back and check it out if you're interested. For our purposes, we just simply load this code, right? So what is a physics problem I want to look at? So physics problem is a variant of the driven oscillator problem that we have looked at earlier, but I'm going to consider a bunch of new cases here, right? So we have looked at that is subjected to a periodic driving external force, right? It's not just a driven external force, but we have looked at the one particular case which was periodic in nature, and then we looked at the special case of what happens at resonance when the frequency of the external driving force was equal to the natural frequency of the problem in question. But actually it turns out that it is of interest to look at more general types of external forces, right? So you could consider a much more complicated external function, and it does not have to be periodic in nature, or it may have a portion which is periodic, and it may have some other parts which are not periodic, and so on. So in order to get some feeling for this and just to exploit the fact that we already have these techniques, and we will look at a few different examples of this kind. So first thing I want to consider is what happens if f of t is a constant, right? And if that constant happens to be 0, right, that is a case where it's an undriven problem. So we all know the answer to this undriven problem, right? So it's just going to give you oscillatory motion. So you might think that, okay, the moment you turn on a constant external force, maybe there is going to be oscillations because of this, the oscillatory nature of the problem, but also this external force is a constant external force. So maybe there will be some kind of, motion which will cause your particle to keep on running away from where it started, right? So let's see whether, this kind of intuition is reasonable, or is there something else which happens. Okay, so first thing, as always, okay, for simplicity, I'm saying that this particle is at rest and at the origin at time t equal to 0, right? So you could consider some other initial conditions, right? And play with this and explore what happens. So as always, the first step is, so this is actually A. So it's the first example I'm considering. So let me call it A. So first step is to non-dimensionalize, right? Pause the video here and figure out your own way of non-dimensionalizing this problem, right? It's a fairly straightforward one, but even so you should do this. So first thing, so my way of non-dimensionalization is the following. I just find the omega scale is easiest for this kind of a problem, which is just square root of k by m, and then I therefore get the time scale, which is just 1 over omega naught equal to square root of m by k, and then the acceleration scale is f naught by m, right? F naught is the external force which gives me a natural force scale, and therefore I get a natural acceleration scale, from which I get the distance scale, right? I mean, you can say that maybe you don't need the acceleration scale. In this case, you can directly go to x scale. It's okay. We'll put this down in the standard form that we have been looking at these problems. So once we have position and time scales, these are the two critical ones, we make the transformation. Wherever you find x, you replace it by the position scale times x, right? So now the new x is actually a dimensionless position in some sense, right? It seems like something contradictory. On the one hand, we are calling it position, but also saying it's dimensionless. So this is just a physicist's way of saying that you're looking at a quantity which is really position, but in such units, so that you have basically scaled away these units. You are just converting it into a purely non-dimensional quantity. So that's what is meant by dimensionless position. There's also dimensionless time, right, which is 1 over omega naught times t. So then you get, as usual, so we'll go ahead and substitute. Wherever we have x, we'll put f naught by k times x. So d squared x is just 1x. It's not, you should not get confused and think that, oh, there's a second derivative, so it must be x squared. It's not x squared. It's just only 1x, but in the denominator, there is going to be t squared, right? So that's what gives me omega naught squared. So m times f naught by k times omega naught squared and d squared x by dt squared, where both of these quantities x and t are non-dimensional in nature, is equal to minus k times f naught by k times x plus f naught, right? So there is an external force which has to be included, and so if you do take care of the algebra, and recall that omega naught squared is equal to k by m, a lot of cancellations happen, and then you get this very simple differential equation. The second derivative, d squared x by dt squared, is equal to minus x plus 1, right? So we find that in fact the final differential equation after non-dimensionalization has no free parameter, right? It's just a simple differential equation involving no other parameters. Okay, so we have already said that the initial conditions are taken to be x of 0 and x dot of 0 is also equal to 0, and which is an acceptable non-trivial initial condition for this problem. So if you had the problem where there was no external force, then this would not be an interesting initial condition to start, right? Why is that? Can you go back and check that and answer for yourself why this would not be an interesting initial condition to consider if f naught were 0, right? Okay, answer this question yourself. Now let's move on. So let's see what happens. So this is a second order differential equation. How do we solve this differential equation, right? So there is a whole technology associated with solving problems of this kind, right? So it involves, first of all, rewriting it as some, the left hand side must have only stuff which involves where an x is present, right? So it's d squared x by dt squared, plus you can have some stuff constant times dx by dt, plus some other constant times x, equal to all stuff on the right hand side will be purely functions of t, right? So this is one way of separating it out. And then you look at the homogeneous differential equation, solve for write down the general homogeneous differential equation, and then you need to find only one particular solution for the full inhomogeneous equation. And then if you just add one particular solution to the full general solution to the homogeneous equation, that in fact gives you the full solution for the inhomogeneous equation. And then you have to just bring in the initial conditions and the two free constants which will come in invariably for a second order differential equation will all get fixed based on the initial conditions. We have two initial conditions, so two constants will be found out and you get the answer. So for this problem, I am not going to take this elaborate process. I will just write down the answer, right? I have worked this out. You can also check this yourself. So it turns out that the solution is simply x of t is equal to 1 minus cos of t, right? It's a very simple solution, and it's quite remarkable that in the presence of an external force, the particle is actually not going to run away to infinity in some sense. It's going to still keep on oscillating about a different origin, right? The only thing that this external force manages to do is to just shift the origin about which this particle will oscillate. So let's see what that means when we plot in a moment. But before we plot, let's use our very powerful toolbox, the RK4 method, right? So in order to send our differential equation into this RK4 toolbox, we must first recast this second order differential equation into a more than one first order differential equation involving two variables, as we have been doing for many problems. We already know how to do this. Is just take dx by dt equal to v and then dv by dt equal to minus x plus 1, and then you have x of 0 equal to 0, v of 0 equal to 0. So in vector form we have this vector which also brings in time, then x and v. X is equal to this vector, and the rate of change of x, the vector f, is given by 1. It's always going to be the first row of this vector f is always 1 because its t dot is just 1, and then x dot is v by definition, and then v dot is equal to minus x plus 1. So this is the problem we are looking to solve, right? So once again we will use the standard code, right? So we have defined this rate function. Rate function is a vector, and it's a vector of functions, if you wish, right? And it involves these variables t, x and v, which all have to be put in with an underscore sign because we are defining a function here, right? And then so let's go ahead and hit shift enter here. So there we go. So initial vector is 0 0 0, time t equal to 0, the particle is at the origin 0 and its speed is 0, so it's just 0 0 0, and the solution we already know is minus cosine of t plus 1. So I will also define a new function which is called solution of t, and now we are of course ready to go ahead and invoke the RK4 function. So data is equal to RK4 of rate from comma initial comma 40. I am taking it up to 40 time steps, and 300 is a measure of the number of iterations involved. So let's quickly go back and recall the arguments that go into this function. So n max, right? So it's just the number of items. If you make that larger, then it's going to involve more operations and perhaps it will give you better accuracy, but I am just choosing it to be 300, right? And I know that this is going to work well. So I'm going to hit Shift Enter. So it has already generated this data for me. I can go ahead and do a list plot of this. There you go. So this is the solution coming out of the numerical implementation. So let me hide this and then compare against my analytical solution. And there you go. So you see that it's perfect oscillation, right? So the solution is, so first of all, there is perfect agreement between RK4 and my analytical solution. And it's interesting that the analytical solution for this problem is also so simple, right? It's just an oscillation. It's going to give you the same cosine t oscillations. If you had f0 equal to 0, then also you just get cosine of t. And I mean, in general, you would get cosine of t plus sine of t, right? So I told you to think about what will happen if you started with this initial conditions x of 0 equal to 0 and x dot of 0 equal to 0 with f0 equal to 0. So you will simply, the particle will just remain at the origin forever. So it's not very interesting. So probably you should choose some different initial conditions if you're working on the problem with f0 equal to 0, and then you will get, maybe you can choose x dot of 0 to be some 1, for example, some other speed, and then you will have oscillations which will be just cosine t plus sine t, right? Some linear combination of these two according to initial condition. But here we see once again that you also get perfect oscillations. There is no tweaking of this. It's just oscillations, and the particle is going to be bounded, and doesn't matter how large your external force is, it's only going to manage to shift the equilibrium position, nothing else, right? So this is what something quite interesting. So if you want your external force to do something more dramatic, right? So you need it to change as a function of time, right? So we saw that, of course, if you had f0 were itself a cosine function, right? That's the problem we considered first. We saw that it could, if you're at resonance, it could give you like really large amplitude oscillations, and it could take a particle, I mean, it's going to keep oscillating about the origin, but its amplitude can keep on increasing. So let's look at what happens if my external force is not periodic, but it is constantly increasing, right, as a function of time. So the most natural function that comes to mind of this kind is a linearly increasing external force. So that's external force, a linearly increasing external force. So we are studying this differential equation, and now we take f of t to be some constant times t. So I have chosen that constant to be a. It's not to be confused with acceleration. A is just some variable. It's a parameter of your system that you can vary. So as always, start by non-dimensionalizing your differential equation, and you can pause the video here, spend a few minutes and work out your non-dimensionalization, and then cross-check against mine after a moment. Okay, so my solution is just the following. As always, I take my omega naught to be just square root of k by m, therefore it gives me t, which is 1 over omega naught. Acceleration scale in this case is at by m, right? So for t, I have to use this t scale, and therefore once I can get also x scale, which is just at by k, right? You can see from this equation that force by k is just position. So I can use this at by k, and then t is just nothing but 1 over omega naught, right? So then with some small manipulation, you can quickly convince yourself that the length scale in this problem is a by m omega naught cube, right? So if I plug in wherever I find x, I must put length scale times x, which is a by m omega naught cube times x, and wherever I find t, I must put 1 over omega naught times t, right? So we are doing this exercise in non-dimensionalization so often, so there's so much repetition of this because we have found that a lot of students are shaky on this, right? Apparently, it's a very simple thing to do, but it throws a lot of students into confusion mode, right? So we're just trying to illustrate here that in fact it is very simple. You just find all the scales in the problem, and then using this technique, not only can you do it quickly, you can also now you don't have to introduce some new variables and all. So that is also one way of doing it, right? You can think of each of these scales and call them by a new label, and then you introduce some x divided by length scale is equal to a new label and so on. But here the idea is you just retain the labels as they are. X will remain x, t will remain t, but you must interpret it right in the end. So what do we do? Wherever we have x, we'll replace it by length scale times x. So we have m times a by m omega naught cube times omega naught squared. Omega naught squared is just coming from 1 over t squared, which is sitting in the denominator. So which is equal to minus k times a by m omega naught cube x plus a times 1 over omega naught t. Right? A lot of cancellations will happen, and we'll be left with just d squared x by dt squared is equal to minus x plus t, right? In the problem that we considered earlier, it was d squared x by dt squared equal to minus x plus 1. Now there is a dependence on time, right? And that is a linear dependence. So what would we expect? So now of course we expect that since it's a force that is an external force which keeps on increasing as a function of time, you do expect that your particle will not stay bounded, right? It's going to be unbounded motion, right? We will see that in fact this is true, but there must be also an oscillatory component to this, right? And so indeed that will also hold out. So yeah, by the way, there is no free parameter left, right? And so we don't have any other knob to tune to change some qualitative aspect of your solutions, right? So just work with this simple problem, solve for it, and then that gives you all the the most general behavior of your system is contained in this problem involving no free parameters. Okay, so we have already taken x of 0 to be 0 and x dot of 0 to be 0. It's not an issue because this external force is anyway going to kick it out of its initial position, so there's no issue. It's just that if you did not have an external force and if you took this form, then it would be a dull problem and it would just lie there on the origin forever. Now this is a second order differential equation which can be solved analytically. So once again, one can invoke these techniques, right? So the solution for the homogeneous equation, the general solution, is just always the same, right? In these kinds of problems, it's just going to be some constant times cosine of t plus another constant times sine of t. So all the variations are coming only from the type of external field which is being applied, and therefore only the particular solution will change. And the particular solution you'll start to see a pattern, right? So in a slightly more advanced course on math methods or some differential equation course, in fact you'll see that this whole class of differential equation, there is very nice, well worked out prescriptions for solving this. There is a way to get at the particular solutions. So here I'm going to once again just give you the answer. It's a very simple answer. So x of t is t minus sine of t. So there is a sine of t type of term, right? Earlier we had a cosine t, it should be there, either a cosine t or a sine t. So in this case it turns out to be sine t. It can be an arbitrary combination of these two depending upon the initial conditions. So it turns out that for this problem it is just t minus sine of t, and t is coming because of the external force. So as a function of time, the position of your particle is going to keep on increasing. Not only is it going to keep on increasing, but actually it's going to increase linearly with time. And then these oscillations only give you some fluctuations about this linear form, right? So once again, the canonical form is just dx by dt equal to v, dy by dt equal to minus x plus t, x of 0 equal to 0, v of 0 equal to 0. All of this information can be encoded in vector form like here, and then we have vector x dot is equal to f, rate function in this case is 1, v and minus x plus t. So I'm going to hit shift enter. Initial conditions once again 0, 0, 0. Solution now has changed. I told you that the solution is just t minus sine of t. So I have the solution here. Once again we invoke the RK4. I continue to use 40, 300. I mean, we can tweak this and play with this. We'll see what happens. Okay, I don't need to make this verbose, but this one I will show you what it looks like. So there you go. So it's a very interesting plot. So it shows you that it has this sort of snaky behavior. It's like the system really wants to oscillate, but then on average it also needs to keep on running away from the origin, right? So there is this external force which is kicking it, and it's going to keep on running away as a function of time. Yeah, so it's interesting that this external field, which is proportional to time, is going to give you also displacement which is roughly proportional to time only, right? Suppose you did not have this dx by dt term, right? Suppose we had a differential equation which only involved an external force, and if there was no harmonic type potential in play, right? If there were no cake, if there was no spring attached to this, then you have to take integrate it twice. So it's going to be actually quadratic in nature, right? So you see that there are two things that this the spring is doing. On the one hand, it's trying to bring in some oscillatory motion, but also it's also reducing your the speed with which you run away to infinity, right? And it's in fact brought it down to linear. Okay, and the final check is of course against the numerics, which we know and expect. Better agree, and indeed, so the two of them do agree, as good a precision as you would like, right? And I'm just using 300, in this measure of number of operations. You can play with this. I'm sure that it will work out even for much smaller number here as well. Okay, so let's do a quick check of what happens if my external force were not linear but quadratic in nature, right? So what do you expect, right? You can pause the video for a moment and not do any calculation, but ask yourself if you can guess how will the system behave in the presence of a quadratically increasing force. Okay, so let's look at the quadratically increasing force case now. So I have f of t equal to a t squared. Now a once again is not acceleration. A is a different constant, different units, and my solution for the non-dimensionalization is soon coming up. So pause your video and work your own non-dimensionalization. Okay. Omega is just the same, square root of k by m, therefore time scale is square root of m by k, acceleration scale is a times time squared by m. Time squared I'm going to use 1 over omega naught squared. X scale is just force by k, which is a t squared by k times 1 over omega naught squared. So I will just write it as a by m omega naught to the 4, right? Earlier I had a by m omega naught cube, now it has just become a by m omega naught 4, and now you see that if I make the transformation x going to a by m omega naught to the 4 times x and t going to 1 over omega naught times t, I will get a string of cancellations on both sides. I urge you to verify this, right? So you'll see that on both sides a lot of cancellations will happen, and crucially what has changed on the right hand side is I have a by omega naught squared because there's a t squared sitting there. And so a lot of these things will just cancel out, and finally my differential equation is a very simple d squared x by dt squared is equal to minus x plus t squared. So once again, no free parameter, right? X of 0 equal to 0, x dot of 0 equal to 0. If I impose these initial conditions, I can of course use the general theory of differential equations of this kind, linear differential equations in homogeneous ones, and I have the technique to solve for it. But let me allow you to guess. What do you think will be different this time, right? So of course we must have something like cosine of t and something like sine of t, and whether you have only one of these two or both of these two will depend on x of 0 and x dot of 0, and also of course the precise form of the particular solution. So in this case, the particular so we saw that when I had just f naught, the particular solution was just a constant. I had a 1, and when I had t, the particular solution brought me a t. And now when I have an external force which is t squared, so what do you think it will be? It's going to be quadratic in nature. So it's going to be, in this case, just t squared. So this is the solution. But in general, actually, the theory tells us that if you have t squared sitting on the right side, you could try out an ansatz like alpha times t squared plus beta times t plus gamma, and then you have to find these coefficients. So there is a technique called the method of undetermined coefficients, and so it basically tells you what is the right type of form you must give for the particular solution, and then you plug that in, and then you can actually extract those coefficients, right? And so then there is some more subtle aspects involved with this, which is, there is this auxiliary quadratic equation that you can write for the homogeneous part, and then if one of the roots of this actually agrees with a certain coefficient on the right hand side, then you have to be a little more careful and so on. So but in general, if you have a polynomial sitting on the right hand side of a certain degree, the particular solution will also involve a polynomial of the same degree, right? So this is something that you might encounter in a full-fledged course on ordinary differential equations. And for our purposes, I'm telling you that the solution for this problem is just t squared minus 2 plus 2 cosine t. You can go ahead and plug this in back into the differential equation and verify that it is true. Okay, so now what should we do? We should recast the second order differential equation into the canonical form involving a first order differential equation of a vector of multiple functions, right? So there is x and v, and I have x dot and v dot, and then not only do I do this, but I have to recast everything, all of this put together including time, into vector form, and then I have capital X dot is equal to capital F, where capital F is equal to 1v and minus x plus t square. That's what has changed. So then we have this rate function which also undergoes this modification. Initial vector remains unchanged. Initial vector is a 0 0 0, and then I have my solution has changed, 2 cosine of t plus t squared minus 2, and then we go ahead and invoke the RK4 function. I'm only going up to 10 this time, right? So you will see in a moment that so this is what the solution looks like. So I mean, it is basically quadratic in nature. I have chosen a small enough t so that I can see the small wiggles which you can see, right? Because t squared is already a sufficiently fast growth that it's actually not going to it's not going to make this very visible, right? So these fluctuations, and then indeed there is also cosine in there. So as we can verify by cross-checking my analytical expression with this, so indeed both of them agree very, very, very closely. So if I make this, instead of 10, if I make this 100, so you will see that it's hardly going to be visible. If I make it 100, and then if I run this, also make this like 80, let's say, and then you see that it basically looks like t squared. So it's very heavily dominated by the external force. But once again, I find it quite interesting that a second order, a quadratically increasing force is giving you dynamics which is also quadratically increasing, just simply because you have also there's a springiness associated with the motion of your particle, and that spring is not so successful in giving it any oscillatory motion here, but it is restricting its running away, right? And it's keeping it at quadratic in time. Okay, so the final example that I want to do here is an exponential decay, right? So if your external force were started off with f naught, but if it were to decay down exponentially, like here I have another parameter alpha in here, then that's an interesting external force to consider. So what kind of motion can you get? Will you Will your particle be bounded? Will your particle run away? What happens? Okay, so let's check this. So okay, so I have to warn you that now the non-dimensionalization exercise here is a little less trivial than the previous one. So pause your video and see if you can come up with two independent non-dimensionalization schemes. I am going to use one, but maybe you should come up with a different non-dimensionalization, solve your entire problem in a different non-dimensionalization scheme, and then cross-check that both the results should agree, right? So this is something that you should definitely do, right? So pause your video, work this out, and then you're ready to look at my solution. So my solution starts simple, omega naught equal to square root of k by m. T scale, I will take it to be 1 over omega naught. Now acceleration scale is f naught by m, x equal x scale is just f naught by k, right? So this is a very simple scheme I have chosen. So what could have changed? What could have changed is we could have taken a different time scale for this problem. So alpha brings in an alternate time scale. Instead of using 1 over omega naught, I could have also used 1 over alpha as a time scale, or I could have used some linear combination of these two, right? Or something like 1 over square root of omega naught squared plus alpha squared, for example, or something else, right? Some very complicated thing. So there are actually infinitely many ways of doing non-dimensionalization, and depending upon the precise details of your problem, maybe one is more convenient than the other, but none of these can be wrong. So I urge you to play with this, try out at least one more and maybe many more non-dimensionalization schemes, extract the solutions and make them all agree with each other, right? So in the spirit of this course is to basically solve simple problems but look at them from multiple angles and reinforce our understanding, right? So make it so solid with simple problems that then automatically new fresh directions emerge, and then suddenly we find ourselves solving new unsolved problems, or problems which may lie in the realm of research suddenly opens up, right? So this is how research also goes, is that you become so strong with what is already known, then suddenly you keep on knocking on doors and some door opens up which actually leads you to something new, and sometimes not just new but something very exciting can also come up in this same process, right? So that's what this course is about. Now making this transformation, I will change x to f naught by k times x, t to 1 over omega naught times t, and then we get this string of simplifications, and now there is a small variation which appears, right? We have d squared x by dt squared is equal to minus x plus e to the minus lambda t. So it's no longer a parameterless final differential equation. So there is a new dimensionless parameter. So you can see that I have introduced a lambda which is actually alpha by omega naught. So it has the same, so alpha and omega naught have the same dimensions. So alpha by omega naught is dimensionless, right? So alpha times t is dimensionless and omega naught times t is also dimensionless, right? So alpha by omega naught is indeed a dimensionless parameter. So there is this one free parameter left in this problem. It's still a completely analytically solvable differential equation, right? So for simplicity, I'm just taking x of 0 to be 0, x dot of 0 to be 0, and the solution, it turns out, I'm just giving you the solution, right? You would expect that the solution will be a linear combination of cosine of t and sine of t, and then because there is e to the minus lambda t sitting on the right hand side, the theory tells us that we must try out for a particular solution something which involves e to the minus lambda t times some constant. So you can take care of all the details and work out. There is a very systematic way. It's not magic that I'm able to write down the solution. There is a very well known and well delineated systematic approach for doing this. If you do it, then you can show that x of t is given by this expression. For our purposes, it suffices if we can just plug this expression back into the original differential equation and check that indeed it holds out, right? Now for the numerics, So you should work out this problem for various different values of lambda. But I'm going to choose lambda equal to 1, but you can maybe use some like a manipulate command, and try out a range of lambdas and see whether the nature of the solution changes substantially. So by the way, the case of lambda equal to 0 is interesting. So what does it mean? If I put lambda equal to 0 in my original equation, lambda is the same as alpha basically in units of this omega naught. So if lambda is 0, that's basically like alpha is 0, and that means basically f of t is f naught. And is this a problem that we already know how to solve? Yes, we just did it in this very module. And then you expect the solution to be just 1 minus cos t, right? And that's what we are recovering this solution. So that's good. And the other extreme is lambda equal to infinity. So in other words, if alpha goes to infinity, you see that f of t is 0, right? That is also a case that is familiar. What is interesting is that both these limits actually give you just perfect oscillations, right? I mean, you won't recover that if you directly plug in here for the reason I told you earlier, which is that we have chosen this special initial conditions which make that problem where if you put f naught equal to 0, if you put f of t is just 0, then it's going to be an uninteresting solution. It's just going to give you x of t equal to 0. But if you try out, so this is an exercise for you guys, right? I want you to check the limit of lambda going to infinity and see that it will reduce to a more interesting solution for the unforced problem, right? By taking x of 0 to be x of 0 can be 0, but let's say x dot of 0 is taken to have some finite velocity, maybe 1, let's say, right? Or in some number you can choose, and then you'll see that work out the solution and then take that limit, and then you'll see that indeed there is going to be a connection to the original cosine t plus sine t. So it's quite nice that an exponential decay function, so there are two limits to this, it's a constant or it's 0, and both of these limits will give us just pure oscillations. So now what happens if lambda equal to 1? Let's look at this. So we have indeed, there is this exponential part which is actually like your transients. So it's like, doesn't matter what lambda is, the system is eventually going to oscillate. It's not going to run away to infinity because the force is simply not strong enough, right? So we know that the two extreme kinds of this type of a force are either it's a constant force, or even the constant force only managed to give us oscillations but about a different equilibrium position, and the other extreme is just no force, and that is the familiar problem where of course you are not going to have anything other than oscillations about the mean. So if you put an exponential decay in time, also you expect that this motion is going to be bounded, right? So this is an argument you could have perhaps come up with right at the beginning itself. So now you will see that now that we have the solution, and we will explicitly check this numerically, dx by dt equal to v, dv by dt equal to minus x plus e to the minus t, and then we recast it in the canonical form, in the vector form like here, and then we have the rate function, initial vector, and then the solution all defined like here. Then we go ahead and invoke the RK4 routine. Let's see what the solution looks like. So the solution looks like here. So indeed it starts off trying to do this exponential decay, but this is a very small effect. It's going to be there only for a very short time. So instead of 100, if I had made it just 10, then perhaps it will be more exaggerated, this thing. So there you go. Initially it seems like, it is going to keep on decaying, but it's not going to fall below a certain value, right? Because this cosine of t plus sine of t will kick in for large t, and exponential of minus t will basically become irrelevant as time becomes large. So if I take something like a 40 time steps, so there you go. You see that it's now basically its amplitude is a constant for all practical purposes. And now if I were to go here and compare this against my analytical solution, I would not be surprised that the two of them agree, and in fact that only adds to our confidence. So what have we done in this module? We have played some games involving external forces of a very simple kind, but which were not oscillatory in nature, and we managed to extract some very simple and very instructive physics out of this. And also we managed to use RK4 to cross-check our results. So by the way, just before I close off, I want to tell you that these are problems which appear in the very famed Landau-Lifshitz series. So there is a very nice book by Landau-Lifshitz on mechanics, but it's a rather intimidating textbook. If you were to just directly go and look into this section on oscillations, you would find these problems. And for a person beginning out in physics, Landau and Lifshitz would be a formidable place to learn it from. And so I'm pretty sure that somebody who, if they're picking up the first mechanics textbook that they picked up was Landau and Lifshitz, it would be quite difficult for them to open up and understand all of this in such a transparent way. So what I have managed to show you is that problems of the level of Landau and Lifshitz, also now that we have worked it out in this explicit manner, everything seems so crystal clear. And so in fact I urge you to go back and try out more problems from Landau and Lifshitz, and even more challenging textbooks. So now that we have this powerful technique, you don't have to suffer through some very difficult algebra, right? I mean, you should do that as well, but in addition you have this alternate approach, cross-check, and then once you have understood it, it becomes easier actually to master the analytical tools. So on that note, I sign off. Thank you.